Hello, this is Captain Chaudhari. In my series of videos on basic ship stability calculations, I was doing bilging. In my last video, I did end compartment bilging. I want to do one intermediate compartment bilging just to prove one thing, that in the calculations there is absolutely no difference whether it is an end compartment bilging or an intermediate compartment bilging. Let us see how. So let us say once again you have a box vessel. Let's take it as 120 meters in length and it is 18 meter broad, and it may be stated that there is a compartment 15 meters in length. Length of the compartment is 15 meter extending from port to starboard, and the forward bulkhead is 20 meters aft of centroid. So if this is centroid and if we say this is forward, this is aft, the forward bulkhead is 20 meters aft of the centroid, that is midships. So it means that this distance is 20 meters and there is a compartment that is of 15 meters length. The ship initially is floating at 6 meters draft. Kg is, let's say in this question kg not given. And the damage occurs to this compartment, and this compartment has got a homogeneous cargo with a permeability 70%. Let's do this question. So we will proceed in the same way. The initial part is loss buoyancy is equal to 15, that is the length of the compartment, into 18 into 6 into 0.7. So that is 5.7. So loss buoyancy is 1134. Right? And now intact water plane area should be total minus loss. But loss always goes with the permeability. So I multiply with 0.7120 into 18 equals minus. Intact water plane area is 1971 meters square. So sinkage will be 1134 divided by 1971 gives me 0.575, 0.575 meters. I'll write these data over here so that I can do the calculations here. Loss buoyancy is 1134 meter cube. Intact water plane area is 1971 meter square, and sinkage is 0.575 meters. So I told you in my last question that one of the first things that you should do in an end or intermediate compartment bilging is to find out where is the new center of flotation. Now center of flotation always shifts away from the damage. So let us say this is forward end, this is aft end, and this distance is 20 meters, this is 15 meters, this is the original center of flotation F, and let us say it is going to shift to this new axis F1. That's it. We take the moment of the area, the water plane area, about the own centroid. So A should multiply with 0. The first term is always 0 minus whatever is the loss. The loss is 18 into 15. 18 is the width of the compartment, 15 is the length of the compartment, and this loss, I'm taking the moment about the centroid of the water plane area, centroid of the total water plane area regardless of damage. So what is the distance from here to here? Now this is 7.5 and this is 20, so 27.5 multiplied by 0.7, because the loss is always multiplied with permeability, divided by intact water plane area, that is 1971. Let's see how much it is. 18 into 15 gives me 2.637. 2.637 is the shift of center of rotation. So this distance is 2.637. So FF1 is equal to 2.637. In this particular case, because you see that the damage is vertically uniform, that means there is no intact buoyancy, there is no watertight compartment. In the entire height till the final water level, you don't have any change, any discontinuity. So we say damage is vertically uniform for the box vessel, and therefore BB1 also will be equal to FF1, that is 2.637 meters. Now in this particular case, we could have said that the new draft being 6.575, we could have said that new KB or KB1 is half of the draft, but actually speaking we don't have to find out KB, right? Because we will not be able to find out GML because the kg is not given in the question. So what we do in this particular case, I will show with the help of a diagram. Like suppose this is the B and this is G, but the ML is a point very high up, and what we say is compared to the vertical distance BG is very, very, very small compared to GML. So we can approximately say that BML is approximately equal to GML. So this is what we have to tell the examiner, that because kg is not given, I cannot find out GML, but apparently GML should be more or less equal to BML, right? So BML we will find out. Now looking at the plan view, what is the moment of inertia? We actually have to find out residual moment of inertia about a athwartship axis through F1, right? So total moment of inertia about F1 should be total moment of inertia about on axis, that means this axis, and that moment of inertia is shifted by theorem of parallel axis to F1 axis. So it would be like this: 18 into 120 cube upon 12 plus 18 into 120 into 2.637 square. This is total moment of inertia about athwartship axis passing through F1. Let us write down 18 into 120 into 120 into 120 equals divided by 12. So I get a figure 2592000 meter raised to 4. So this is the total moment of inertia about F1 axis. Now this is 1. Now what is the loss about on axis? Like the water plane area is damaged in this portion, so loss about the on axis is 18 into 15 cube upon 12. Of course we will multiply with permeability later on, but let us shift it to this axis first. Now original distance is 27.5. 27.5 plus this distance, that is 2.637. So gives me 30.137. So distance from here to here is 30.137. So when I shift the loss to the axis passing through F1, the distance involved is 30.137 and the area is 18 into 15 A multiplied by D square, 30.137 square, and the whole thing has to be multiplied with 0.7 because loss has to be multiplied with 0.7. Let's see how much it is. 18 into 0.7 gives me 176,719.627. Okay, so this is 2. Let us do 1 minus 2. So you get 2, 4. Okay, this will have to be, that is 1 minus 2 will have to be divided by intact underwater volume. So that is 120 into 18 into 6 divided by. So what I get is 186.364. 186.364, and this is BML, which we had said that is approximately equal to GML. So let us find out the trim change now. The trim change is equal to LBP, that is 120, into BB1, which is 2.637, divided by GML or BML, that is 186.364. So 120 into 2.637 equals, divided by 186.364, gives me 1.697. So that is 698. 1.698 is the trim change. TRA should be equal to 1.698 multiplied by LCF. LCF, now this is forward, this is aft. You can see that the LCF has increased. Original center of flotation was midship, so LCF was 60, which is increased because the center of flotation is shifting forward. So LCF, new LCF will be 62.637, 62.637 divided by LBP, that is 120. So let's do this calculation into 62.637 equals, divided by 120, gives me 0.886, 0.886 meters, that is the TRA. So to find out TRF, I subtracted from TRC 1.698. That gives me 0.812, 0.812. So the final calculations will be the initial draft forward and aft is 6 meters. Bodily sinkage is 0.575, 0.575, that is always plus. Now damage is forward or damage is aft. In this particular case, damage is aft. So TRA is going to increase, and if TRA is plus, TRF has to be negative. What is TRF? TRF is 0.812. And what is TRA? 0.886. So 6.575 plus 0.886 gives me 7.461, 7.461, and here it is 6.575 minus 0.812 gives me 5.763, 5.763. So here, compared to my last video, if you have seen in this video, practically there is no difference in working, right? We have to draw the diagram. Please remember, the diagram should be part and parcel of your numerical. If you want to do numerical without drawing the diagram, I'm sorry, you will never be able to master the numerical. So the forward draft 5.763, aft draft 7.461.